So, okay. So welcome everybody. Thanks for being here today. It's a great pleasure to have Mireille visiting us today and giving a presentation. It's her first talk in a while, and took me like 2 years to convince her to talk in public. So that's kind of a world premiere. And she was my PhD advisor, one of the best PhD advisors that I had, because I had like one. And yeah, she's also, so she's full professor at the University of Nice, which is now named Université Côte d'Azur because it's like more classy. And she's also, so she's full prof there, working at the Faculty of Engineering in the Computer Science department, and she's also chairing for CNRS, the National Center of Research in France, the software engineering community. So she's like trying to steer 400 researchers in software engineering working together into doing stuff, which is kind of a full-time job. And then she's visiting us for a week. She will be giving the presentation today, and she's here until Friday 3-ish. So if you want like to meet her, discuss with her and stuff like that, just like manifest yourself, and that will be good. Thank you. Floor is yours.
Thank you.
I think the mic is muted. Yeah. Flash. Should not.
Is that set up the right microphone?
No, look, the mic is working. Apparently.
Down, once you put down, she give you the option which mic you put down.
Yeah, it's using the
that's
one.
Yeah, that's correct. You're good to go.
Okay.
Okay, good.
Okay. Thank you for the opportunity to share feedback on a development that has taken place over several years. I will not present me as Sebastian do it better than me, but here is where I live. Nice place, wonderful place. We should all move there.
Sebastian, what were you thinking?
The purpose of this presentation is to tell the story of a journey that is not yet complete. This journey aims to help non-data scientists build suitable ML pipelines. And many people have been involved in the journey. With Frédéric here, we senior researcher in data science. We have been carrying the project since its origin. And Sebastian worked on the emergence of the first platform. I have the chance to share my experience in the trenches with him regularly. Okay, before we get into the trenches, let's look at machine learning pipelines. In most courses, you will find a diagram like this. Defining an ML pipeline is relatively simple. You select your data, you prepare it, you transform it to match the targeted algorithm, you train the model, you evaluate the model's performance. But depending on your data, you will have to choose among many possibilities. Then you try and try again until you are satisfied with the performance. Okay, let's take an example written in a notebook. Concretely, here is a simple pipeline in a classification context. The code will not be readable. They only allow partial visualization of the pipeline content. First, we start by separating the data into two sets. The data we learn from and the data on which we verify that the model predicts well. Next, we train a model to produce an ML model. Here we normalize the data, augment it to have more data to learn on, select the features to learn on, and then encode the categorical features into numeric. Then we learn with an SVN classification algorithm. This last step produces the ML model. Next, We validate or not the produced ML model. We prepare the validation data, then predict and verify our prediction using F1 score as a metric. Okay. Here is a problem I am addressing. If you are not a data scientist, you will use various online tutorials close to your problem to build a suitable ML pipeline. But it is then difficult for you to identify the limits of the solution. For example, a classical case of error consists of evaluating a model performance by its accuracy while your data set is not balanced. Could we help non-data scientists build pipelines that fit their problem? So it's no longer about replacing a data scientist. It's about helping a non-data scientist to build a pipeline adapted to our problem. Let's start with the context of this development. In 2015, we realized that producing a machine learning pipeline to answer a particular problem is a challenge for a non-data scientist. Even for experts in the reality of industrial applications, the different choices remain difficult to make. There is no one algorithm or even one pipeline that solves all problems. However, in many case studies and tutorial, we have the information that you need to know what to do. So we have the basic of a product line. If we are able to capture the domain, we can generate the solution. Thus, a user will only need to specify the data from which she wants to predict and her goal, and the system can automatically generate the suitable workflow. Therefore, the creation of a product line of ML pipeline has begun. It took 4 years to build the product line aiming to help users create their convenient machine learning pipelines. We named it ROCKFlows. So we started with this initial goal: generate the ML pipeline that fits your problem. I chose to tell you how our goal evolved over time. I know that we usually only tell the end of the story, but this time I think it's interesting to present the story anyway, maybe just to avoid making some of our mistakes. Sebastian used to say, "Isn't your solution the problem?" This remark has probably been through on many occasions. Yet I see some of the mistakes in many developments today. So I propose to tell you some of the significant steps of the journey and then conclude with our current research. First step, let's start the journey. We limited the scope of the software product line to classification. A feature model captures all the information about the domain. The assets are the algorithms, while the product are the generated pipelines. If you are not familiar with the vocabulary of product lines, the feature model corresponds to a set of logical rules between the concept of the domain. The assets are the elements allowing the generation of the codes, while the product are the generated codes. We therefore use model-driven engineering to facilitate the integration of new algorithms and criteria on business requirements. For example, we have separated the feature model from its visualization to manage frequent evolution, mainly associating questions with features. We reuse this approach in 3 different projects. Okay, now, when you are faced to a new project, to a new problem, the system proposes only the valid pipelines. Nice. It is exactly what we wanted. Okay. But we then realized that in the generic case, we could not answer the question, what is the best pipeline for my problem? Too many pipelines remained possible, and we could not sufficiently restrict the space of possibilities by logical rules. Improving on the approach presented in the cited article at the bottom of the slide, we then chose to rank the pipelines on several dimensions to help the user select one. At this stage, we know how to manage pipeline families. Now we will focus on comparing pipelines to help select one of them. To help choose among all the proposals, we decided to rank the algorithm according to their model size, training time, and accuracy performance. We then generalized the experiments by tenfold evaluation and compared the results with statistical tests. Now, end user can choose suitable pipeline whose overall performance evaluated on more than 100 datasets match their needs. Okay, the architecture now includes a set of algorithms and many experimental results. But we observe that the performance of pipelines is very different from one dataset to another dataset, but also from one data preparation to another one. And due to the large number of parameters and remaining valid combination of algorithms, data scientists cannot explain all behaviors. So at this step, beta learning appears to be a practical solution for predicting pipeline performance. We dropped pipeline ranking, which was also okay. Third step. Okay, now we are able to compare pipeline, but we are not sure that how they perform on a particular data set. So we are going to ask the machine to learn from past experiments. Therefore, to enable an automatic selection of ML pipeline, we chose to build a portfolio of pipelines. Several pipelines are grouped in the portfolio, while meta-learning is used to predict the performance of the most appropriate pipelines for each problem case. The principles are as follows. We create new training data set from metadata about data sets, pipelines, and past experiences results. Then we train a model for each pipeline. Now, when faced with a new problem, we consult all these models to predict the values of the three metrics. At this point, we have many algorithms and dataset composition to study. To be able to compare the corresponding experiments, we must perform them in the same execution context. We have therefore moved to a more systematic approach. We set up a dedicated domain-specific language and Docker-based experiment platform to make meaningful learning between experiments, simplify data collection tasks, and automatically trigger meta-learning. Okay. In 2020, ROCKFlows was deployed. We answered the question, what is the best pipeline for my problem as follows. The best pipeline is a valid sequence of algorithms for training. This means, as far as we know, the preconditions are verified throughout the sequence of the target datasets. The problem is not directly characterized by the data, but by its metadata. The requirements are expressed in terms of data scientists, and the performance is defined in terms of three metrics whose predictive value is obtained by meta-learning on 100 reference datasets. In conclusion, we did it. Okay, the work presented here is a result of many collaborations and a lot of works. Okay, we are in 2020. With the pandemic, development stopped for 1 year. In 2021, we changed direction and the journey continues. Now I will go quickly to the new project named ROCKNRoll. The company as a co-contribute to this new project, and I am only presenting the tracks we are following now. Now, let us focus on the learning flows themselves, not on the learning flows themselves, but on the process of building these flows by humans. The first important part of the work is to analyze your data, to compare it with the literature, and to compare it with existing solutions or new algorithms. This first step is time-consuming. Once you have chosen machine learning component, you move on to training and validation. Then we loop until we get the expected result. Here, each iteration is costly, not only in time, but also in terms of resource consumptions. Once we have trained and validated the model, we move on to testing and deployment. We now return to our initial problem with a new look at how to help build the pipeline. The most important part of the selecting one solution is understanding why this solution is well adapted to our problem. So we must before understand what defines our problem. And we know, in fact, the metrics do not define the problem. They are part of the solution. Depending on the study case, the performance to be optimized are not the same. If your model is embedded, its size is an important criterion. If you analyze signal from an engine test chain, you cannot raise false alarm too often. If you are looking to detect raw classes, you cannot use accuracy as an evaluation criterion. We should not choose a metric a priori, but according to the problem to be solved. Meta-learning allows us to expect the same results, but not to understand why a solution was chosen. So let us ask data scientists why they chose a solution to a given problem. So I asked different data scientists why they chose a solution. And their answers are most often difficult to formulate for them and to interpret for me. It was like, I like this algorithm, I know it very well. I found it inside a book and it seems to match my problem, and so on. On the other hand, if you ask them why they did not choose another solution that seems to be well suited, the answer seems easier to formulate for them and to exploit for me. For example, they allowed us to highlight new criteria. That is something that we forget when we analyze the problem. and also past mistakes, that is some shows that were not valid. So to ask this question systematically, we have defined class of equivalences on the data set, the business requirements, and the solutions. Class of equivalence on the three parts. Our goal is therefore to question the data scientists when we detect applications that seem to correspond to equivalent problems, but whose solutions are different. It may not be the same problem. And so we can extract new information. Therefore, we have chosen to work on detecting anomalies in time series. ESACO is working on that subject. And the user of the system will be students beginning in data science. Our first objective is to verify the approach's interest by forcing the problem's analysis rather than looking for a solution by trial and error. Our second objective is to demonstrate that our approach allows us to highlight relationship between problems and solutions. Working on detecting anomalies in time series makes it crucial to understand what scientifically characterizes a problem. I do not take the time to detail it here, but if necessary, I could say more later with the limit of my knowledge. Here are the principles of ROCKNRoll. From the previous application, we incrementally extracted knowledge that we captured in a feature model. We distinguished three spaces in the feature model: the business requirements, the data, and the solution. This is important for the continuation of the approach. Rules on constraints between this space ensure that feature model incremental evolution. We exploited knowledge to analyze new problems and generate notebooks. We are working on notebooks, the generation of notebooks. Then we register the applications, that is to say, the code and the configurations. And we exploit these applications to help the user find past applications that correspond to our current context. So we changed of approach. The source part of the feature model allows finding the associated articles and the authors. We studied 19 applications. The first 10 were from the literature. The next 5 came from industrial applications from the company ESACO. And the last 4 were extracted from OpenML. At each step, we determined the equivalent classes to identify the applications that presented equivalences of problem or solution. With the help of data scientists, here are some examples of how we acquired new knowledge. We identified new criteria, constraints, and what we did not expect, a case of useless variabilities. That is something that was too detailed and it was useless. So we think that the approach is promising. We are currently working on coupling it with metrics such as feature model coverage analysis to improve knowledge discovery. We still need to improve our tools because characterizing the cases identified remains difficult as each application is so complex that there are a lot of features to analyze. And we hope to be able to have data scientist students who will use this new version of the tool in October and run their experiments online. Okay, before concluding, let's make a quick point. We know that we must continuously learn because data science knowledge is being built not only by creating new algorithms, but also by understanding new problems. However, Fran and I are convinced of the extreme danger of letting the machine learn without us really understanding the problem, especially without asking the question of the relationship between our use of the resources and the actual gain. So for me, it's an important lesson for me. And the second point is, in ROCKFlow, we add a systematic approach to feedback through metrics. The metrics may or may not reinforce the quality of our prediction. Also, we worked closely together. We did not have the means to get systematic feedbacks from data scientists. We lost a lot of implicit information by this way. Today, we have that we need to learn ourselves for the machine to learn well. And to achieve this goal, we need to bring data scientists inside the loop. So there is still a lot of exciting work to be done on our ability to capture scientific knowledge yet to be discovered. In this quest, I've shared an agile approach by telling you some steps of the real story. No, I can try to answer your questions, but I am not a data scientist. Fortunately, I know a few indeed, and thank you for listening. And if you have questions.
That'd be great. The software product line part at the beginning, I'm just interested in how you actually did it, like what technology you used. I know it wasn't the main focus, but
yeah. I didn't speak about that because technology was also an error from my point of view. Because we have a lot of web services, it was written in Java. Some part was written in Python because there was a lot of people who worked on this. So the main part was Java. We were connected with SPLA to manage feature models. The interface was AngularJS. The platform used Grafana, a lot of things because we Python, too many technology for data for researchers in software engineering.
But that wasn't the main focus. You wanted to get that done so you could move on to the next.
Yeah, and I hope to change to have less technologies and something more unified and also more easy to manage. I don't think that the technology was not the good choice, but it was not the good choice for a researcher because I have too many time. I didn't have time to manage all that.
Question about the continual learning component that you mentioned. And I'm wondering, like, what are besides the need for a human in the loop, are there structural components that are essential for like avoiding forgetting things that were known in the past are not necessarily relevant at the current time?
Okay, I'm not sure to exactly respond to the question, but I will give my point of view on this subject. I think you are right. It's a real big problem, and even more in machine learning, because it seems to me that a lot of lessons are lost. So, for example, one mistake that we had, as we have a lot of experiments, and we had some results that contained NaN with, and we didn't see that. And sometimes I try to justify what I did, and I discovered that inside my data. So what we did is we introduced what we call a justification diagram, whose the objective is to automatically always verify what we know that we have to verify, and to get evidences that show that, yes, we did it. So but I think it's really important. I don't have that in the new system as we are just beginning, but I think you are totally right. So, yes.
We have a question in the chat from Richard, who can't unmute himself because of the cats. So he's asking, did the data scientists have any requirements about traceability between their data inputs and the outputs of the workflow?
The system is not for data scientists. I don't know if for the moment, I don't have this ambition. I'm not sure that they need something like that. They are so clever, so that they don't need that. And almost if they are researcher in data science, I can't help them because they have so much to do that it's not possible. But if we need traceability, I think it's a good question. Yeah. Well, okay, I have a beginning of response. When we select in the configurator, this one you see here on this part, here you see the constraints that are triggered by your selection, and this is a beginning of response to this question because you selected that your value, you have missing value at random. Some constraints were triggered that says, okay, so no, you need to make that. And so we are expecting you to have data in this state and so on. And so it's just a beginning. It's not really satisfying, but it's a beginning. It's good for Richard?
Yes. But you can talk at lunch.
I have a question from the PhD student in computer science, and I'm really appreciative for your presentation. And I understand that you want to help some non-data scientists to apply the machine learning pipeline. So one of my questions is that even if that you have to set up in your program or in your work, set up some specific format of the inputs, for example, like a categorical things or relational tables or figures or images or sounds.
Okay.
What kind of tests we can help?
Okay, we don't work on images. We work on images for a moment, but we are not doing that only structured data for the moment. If for ROCKFlows and for ROCKNRoll, we I don't know. I don't know because as this is time series, I saw that Yassine is a PhD student who is working on, he's data scientist, transforms the data, but I don't know if the transformations are inside the tools or outside the tools. That's a good question, sorry.
Thank you very much. I'm a good guinea pig for this talk because I know very little about it. So what's the political comeback, excuse me, from people working in machine learning where, excuse me, from what I see, a lot of people are trying to use machine learning because they don't want to understand the problem.
Oh, yeah.
So,
Oh, yeah, totally agree. I have a slide that I removed about that. We try to ask the machine to learn something that we know. And we did it. So I totally agree with that. But Frederic, who used to work with me, he dislikes this approach, and I am convinced that we are destroying the planet if we continue to learn anything for nothing, and if we refuse to before understand what is the problem before to train. So I think it's really important. Okay, I totally agree with that.
hopefully we can talk more later.
Okay,
Also,
but Frederic, who is very eminent researcher in data science, is aware, is totally, he agree with that. But we have to, it doesn't mean that we don't have to make machine learning. Yeah.
Yes. I think we agree. I have a comment on the metrics. A lot of the metrics that we work with in software engineering, I've learned that I don't really believe them all the time. And it seems that the metrics that you're using here are sometimes critical to what you're trying to achieve.
Yes, I think that's, and Frederic agree also like that on that. Metric for machine learning, yes. I think that will be the first thing that we will test with students is our ability to learn them, to teach them what metric to use according to their problem. It's one of our first objectives because it's really a problem because they used to use F1 score. No, because before they used accuracy, no, in the last year they used F1 score, but we are not sure that is a good one. And so what is really interesting is that detecting anomalies in time series implies to use other metrics because variabilities of the problem. So we will try, but you are right also.
So, last question. Is there always a metric that you think is suitable? Or
No.
Sometimes there's no metric that you can use.
No metric?
Yeah. That you think is exactly right for your particular problem.
I don't know. I never think like that. So and I have to ask to data scientists.
Yeah. Thank you.
Do we have questions? Here or remote? Okay.
Thank you.
So let's wait for 20 seconds for someone to manifest. They should have a message on the chat. So maybe you should wrap up. Thank you very much.
Thank you. Thank you very much.
And so if you want to discuss about anything related to software engineering, software design, composition, data science, and stuff like that, it's here until Friday.